Okay, well, welcome to the Winds and Currents webinar. Today, we have Christine Gommenginger, who's going to talk about imaging small-scale ocean dynamics at the interfaces of the Earth system with the SEASTAR Earth Explorer 11 mission candidate. So welcome, Christine. I'll let you take it away.
Thank you very much, Sarah, and thank you very much for the invitation to come and talk to you today about SEASTAR. So I'm Christine Gommenginger. I work at the National Oceanography Centre in the UK, and I am going to talk about this mission candidate to Earth Explorer 11, which I am leading with a number, many of you who are online may already know about this. So I apologize in advance to those who may have seen some version of this talk in the past. But we have a kind of mixed audience of people who know very little about SEASTAR and some who know everything about it. So I apologize to those who already know a lot, but it's worth going through the really to give the context of this new mission. So this is the outline of what I'm going to talk about today. So first of all, SEASTAR and the Earth Explorer 11, just a few words about what that means. Then I'll go through the SEASTAR mission itself, going through the science drivers, the mission objectives, products, requirements, etc., etc. So the details of what we are proposing, and then some results from some airborne campaigns that we have performed in the last year. So to start off with, so Earth Explorer 11. So this is in the context of the European Space Agency. So I'm aware that NASA is now using the Earth Explorer kind of terminology as well for some of its mission calls. So it's going to get very interesting and very complicated about when we talk about Earth Explorers. But essentially, the Earth Explorer in the European Space Agency has been running for many years, and it's the kind of flagship program within ESA for its science-driven missions. So missions like CryoSat and SMOS and GOTCHE and so on have all been Earth Explorers in the past. So Earth Explorers are driven by scientific excellence, underpinned by innovative technology. So that's the kind of short summary of what they are looking for. It's open to anyone, but it must be led by a scientist. And increasingly, it's not just about the science, but it's also about the societal benefits of the mission and the data it provides. So Earth Explorer 11 specifically, the call came out in May 2020 with a deadline of 4th of December 2020, so quite a while ago now. And I proposed SEASTAR to Earth Explorer 11, accompanied by a group of co-investigators, some of whom are actually on the call today. The proposal altogether wasn't huge, maximum of 30 pages with references outlining essentially the science case, technical concept, and giving a rough order of magnitude cost for it. The key boundaries, for those of you who are interested in these things, the key boundaries for the call was for mission total of 450 million euros, of which 250 are for the space segment. The launch window for this would be in the 2031-32 kind of time frame. And really, it is of interest to those who've tried to fit satellites into launches to know that we are tied to either an Ariane 6 or big SE launcher, which may seem like a trivial detail, but when your satellite becomes big, this becomes an important driver. So the outcome of E11 was that 16 proposals were submitted, 4 were selected to enter what is known phase 0. And SEASTAR is therefore one of 4 candidates that are currently undergoing these investigations in phase 0 to increase the level of maturity, scientific readiness levels, and technological readiness levels. So this is a figure which I'm sure many of you will have seen before, because I like to use it as illustrating really what SEASTAR is about. So this is a a satellite image from Sentinel-2 taken in the Baltic Sea, showing these sort of swirls and eddies and filaments at very small scales. You can see the scale there, 10 kilometers. So, and really this is what is driving SEASTAR, is to try and get observations of the surface dynamics, ocean surface dynamics, that may be responsible for some of those patterns that we see. In this particular case, of course, in algae blooms. And we often see these kind of small patterns near jets and near eddies, and particularly in coastal and in polar seas as well. There are very few observations of these dynamics at these scales, because it's very difficult to get this sort of synoptic images of what is going on from in situ or kind of methods. We know from numerical models that these small scales are very important. They have a major impact on the global ocean circulation and climate, and particularly this sort of ageostrophic circulation and the interactions between the winds and the waves and the currents at those very small scales is believed to be very important for example, the vertical exchanges of between the atmosphere and the ocean of heat and CO2, etc., etc. And then more recently also, there has been more work showing that these small scales also affect the pathways of horizontal dispersion. So things like, for example, how oil spills will disperse. It seems to be driven very much by those small scales as well. And then finally, there is currently no existing satellite data that can provide the measurements that we want at those scales. And there's no planned missions either that provide this sort of spatial resolution, accuracy, and the space and time sampling we need to study these processes, which are not just small, but also very, very fast. So, as I mentioned, we are interested in monitoring this sort of two-dimensional fields of surface dynamic, ocean currents and ocean winds, and particularly how these 2D horizontal structures may relate to what's happening in the vertical structure. And this is an example taken from a high-resolution numerical model showing how the 2D and 3D current fields and vorticity fields in this case compare in different seasons. So this is something which we are very interested in providing a new insight about, because of course there is very little data at present to validate what the models are actually telling us. Sorry about that. And then lastly, we have particular interest in what's happening at the interfaces. As I said in the title, we're very interested in interfaces of the Earth system. So the interface between land and the ocean in the coastal zone, the interface between the sea ice and the ocean in marginal ice zones, because of how these small scale processes are impacting transport in those regions, with some very significant scientific and societal interests in understanding these processes better. And as I already mentioned, there are very well documented examples that show that data currently available, for example, from altimetry and scatterometry about currents and winds, are just not able to provide the accuracy and the resolution that is needed to capture these processes correctly. And of course, in the case of altimetry, the fact that we don't actually capture the full currents, just the geostrophic currents, and these processes include a significant ageostrophic component as well that are important. So SEASTAR, the mission objectives that are derived from those motivations are outlined here. And so what we are aiming to do is to measure for the first time 2D images of total surface current vectors and ocean surface current vector winds at 1 kilometer resolution with high accuracy. over all coastal seas, shelf seas, and marginal ice zones. So the things that are highlighted in bold are kind of highlighting the novelty, if you like. So the 2D imaging is something which is of particular interest. The fact that we are measuring total currents and we are measuring current vectors as well as ocean surface vector winds. The 1 kilometer resolution is something that comes out of the numerical models, which show that dynamics change quite significantly when you reach these types of scales. And then, as I already illustrated, the focus particularly on coastal, shelf sea, and marginal ice zones, which is where a lot of these activities are concentrated. The second derived objective from this is really to characterize the magnitude, the spatial variability, and the temporal variability of these processes on scales going from daily to seasonal to multi-annual. So again, this is quite novel in the sense that we are looking at the full scale of variability from very short to seasonal and longer, to try and understand how these processes evolve, both in a sort of short term to longer term. Sorry. As the derived products from those total surface current vectors and ocean surface vector winds, wind fields, we want to derive higher order derivative products like gradients, vorticity, divergence, and so on, because of in order to investigate that relationship between small scale phenomena and vertical exchanges between the atmosphere and the ocean interior. Linked to this is the relationship between those small-scale dynamics and marine productivity, using, for example, synergy between the data from SEASTAR and what we see in high-resolution satellite images, particularly of algae blooms, but also SST and other microwave data. And then finally, of course, the modeling aspects. We are doing this very much to provide new observations, to validate the high resolution and coupled models, and to support the model developments and developments of new parameterization, so that we can actually improve our forecasts and reduce uncertainties in climate projections. We have a number of secondary objectives as well, which I will go through relatively quickly. One relates to sea ice drift vectors, in the sense that if we can measure ocean currents, we can also measure instantaneous measurements of sea ice drift vectors, which should give us a bonus compared to what is possible to do today. A secondary objective is to look at improving the understanding of directional ocean wave spectra by looking at the higher frequency end of the ocean wave spectrum, looking at shorter waves and the impact of fronts, wave breaking and at fronts and Langmuir cells and so on. So very high resolution kind of processes, which we are not really able to look at very well at the moment. And then lastly, because of this focus on coastal, is try to push it towards the coast into the estuaries, and really looking at the dispersion of river plumes in the coastal zone, and see if we can say something about the fate of, for example, terrestrial input into the ocean. So that's it for the objectives. The products that derive from this are, as I already mentioned, the current vectors and the surface winds. So we are aiming to get data over one continuous swath of at least 100 kilometers. And the key requirement there for us is this insistence on the 1 kilometer resolution, or indeed finer, which we know is something that we really need to achieve with this mission. And the uncertainty at 1 kilometer resolution should be better than 0.1 beat per second, or 10%. So these are extremely challenging requirements, as you might imagine, from space, but that is very much what differentiates SEASTAR from some other missions that have been proposed. In terms of coverage and space-time sampling, well, the emphasis on resolution usually comes at the cost of coverage, essentially. And our focus, as I said, is very much on coastal shelf scene marginal ice zones. This shows the so-called COSMES, so the coastal and shelf season marginal ice zone mask in blue, so all around the coast. We are missing out here a lot of islands, so this is really a preliminary definition of the mask where we will be measuring. That will be, it was a preliminary definition simply for the sizing of the system in the first instance. And then on top you see those little orange boxes, which is essentially the realization that we also want to take some measurements over the open ocean. Although I just noticed some of these boxes must have moved because I have some in the middle of Africa, which is not intended. It's not intended at all. But really the idea there is also to acquire some data, not just also in the open ocean, particularly in areas where we may have campaigns or long-term in situ monitoring type experiments taking place. In terms of time sampling, so this is where SEASTAR really comes into its own, because it's an independent, dedicated mission. We really have the flexibility to choose the time sampling that we need to address our science objectives. And so at the moment, this is something which is still very much in discussion. So originally the plan was to have a fast repeat phase of 6 months, very much like SWAT is currently doing in its one-day repeat. So aiming to have a fast repeat phase for 6 months with a one-day repeat over 15 fixed tracks, essentially, and along each track, and each day acquire 150 scenes, each 250 kilometers along track. But this has kind of evolved as the mission definition has matured over the last few months. And we're now looking at a slow drifting orbit, which may give us the means to achieve a one-day subcycle and the ability to observe the same area on multiple consecutive days without being fixed to a set of 15 fixed tracks. What this means is that with a large overlap between successive images, we may be able to get time series of data essentially over the full COSMES, over the lifetime of the mission. And also to sample those COSMES at different seasonal stages as well. So again, this is still very much a work in progress, but it's a very exciting kind of prospect where we may have a capability to move in and out of either a repeat orbit or fixed or slowly drifting orbits by changing the altitude just very slightly. So it's a very interesting kind of capability for the mission that opens, new potential to look at these very fast varying processes. Okay, so a few words about the payload. The principle behind SEASTAR is based on a long track interferometric SAR, synthetic aperture radar. So it's a radar operating at Ku band. It's a single satellite, so it's not you may have heard of Harmony, who is doing some long track interferometry as well, but using 2 satellites. SEASTAR is just 1 satellite using, and this is so the diagram schematic illustrating the observing configuration. So we have 3 azimuth directions in which we're measuring. So we have 2 pairs of antennas. So we have 1 pair pointing forward of the satellite, 1 pair pointing back, and 1 broadside antenna. So that gives us 3 azimuth direction in which we have both measurements of microwave backscatter and Doppler measurements. And what this allows us to do is, by combining this information, is to actually retrieve both the current and the wind simultaneously. And of course, because it's a SAR, we'll have the high resolution images as well for all of these, from which we will extract information about directional wave spectrum. Now, just to give you some idea, obviously the system is still being defined at the moment. We have two industrial teams working in competition with each other, if you like, currently defining the details of the system. But really, just to give you an order of magnitude, this is sort of typical length of the antenna that we're looking at will be of the order of 15 to 20 meters. That is a very large antenna. It's a very large, long and thin antenna, which brings its own set of challenges when it comes to stability and also mass, and how to fold this into the launcher. So it's definitely an Earth Explorer. It's stretching the envelope in many ways. It's large, it's heavy, it's power hungry, produces lots of data, and all of that adds to it being quite an expensive kind of mission to fit into the Earth Explorer envelope. And that is by far our biggest challenge, is really to squeeze into the funding that is available for Earth Explorer 11. As I mentioned already, a long track interferometry is a very well-established technique which goes back a long time, and there's been a lot of experiments of the standard long track interferometry in the broadside direction, including some in-orbit demonstrations in the past from SRTM or Tandem X, for example. And like I said, we have two pairs of antenna looking 45 degrees forward, 45 degrees backward, which gives us the two lines of sight of the components of the surface motion, essentially. And from that, you can recover the surface motion vector. And this all comes from, it was inspired by concepts called like wave mill, for example, or the dual beam interferometer, which some of you may be familiar with. There are some key differences, is that unlike wave mill, for example, we don't have a cross-track interferometry baseline, at least not a deliberate one. So a cross-track interferometry is what SWAT uses to do sea surface height mapping of sea surface height or water levels. We are doing interferometry in the other direction, if you like, a long track. And also, unlike other concepts like DBI, for example, we're looking at more moderate incidence angles. So we're looking at sort of 20 to 50 degrees incidence from nadir. Like I said, we're adding a third broadside, third look broadside, in order to get the unambiguous retrieval of currents and wind vectors. And finally, something I haven't mentioned yet is the fact that for the broadside, we're also going to have some polarization capability. And this is something we want to use to look at the impact, for example, of wave breaking at the fronts, because of the very fine scales that we're going to be able to resolve with this instrument. So airborne demonstration, we have made quite a lot of progress on this. We have worked, some of you may have heard me talk about this in the past. Some over 10 years ago, we had this wave mill airborne proof of concept, which we flew over Liverpool Bay in October 2011. And there's a number of publications from this that demonstrated the principle for a two-look system, where we obtained some very good results for current retrieval within the 0.1 meter per second by comparing with data from HF radar, for example. And it's taken us 10 years, over 10 years, to get a new system called Oscar, which was finally flown for the first time in the scientific campaign last May in 2022. So it's been a very long wait here, of over 10 years of waiting for this new system to become available. But finally, we managed to fly it. So this is what you see there in the middle photograph. This is Oscar, the airborne demonstrator for SEASTAR. So unlike wave mill, Oscar is a three-look system operating at KU band. So it's very much a like for like demonstrator for what we're proposing to fly in space. And like I mentioned, the campaign that we flew was over the Iowa Sea, which is just west of Brest, which you see there on the in the lower panel. And all those blue tracks that you see everywhere are some of the flights that we have performed. So this data has only recently been fully processed. So we are really just at the stage of getting the first results from this campaign. But so far, the instrument has seems to be giving some really good results. It's very exciting. So one reason we chose this area, so this is an image from Sentinel-2, just west of Brest, which is around here somewhere. And you'll see this island, Ouessant, or Ushant in English, Ouessant, just west of Brest, which is an area with this really strong dynamic currents, tidal currents, washing through the sort of archipelago of islands. And we were very interested to see whether we were able to see some of these in the airborne data. But we also have a second site further to the south here with a mooring, which we have used as a basis for this sort of star pattern or cross pattern flight, which is going to give us a fuller opportunity to validate the data against the in situ data. This is a picture here on the right of a spaceborne SAR. So this is actually S-band. And you will see this again in a moment, but really just to show that these patterns, those patterns we see in the Sentinel-2 image is also very striking patterns in the backscatter that we see from these SAR images over the same area. And so this is where we flew. This is where we flew Oscar, and this gives you just a snapshot of the scale of data that we have from this. So you can just see that ground track of that airborne flight I'm showing you data for, and you'll have the intensity and coherence and interferogram for the aft pair of antennas, for the broadside and for the fore. And what all this gives you when you finally combine all these data is measurements of radial velocity. And when you project this all back into a geographical kind of frame, reference frame, you get this kind of image. So we recognize here that island of Ushant, and this is now the retrieved surface current velocity after correction for wave Doppler bias, Doppler wave bias, which is another phenomenon in microwave Doppler measurements, linked to the velocity of the scatterers that are responsible for the backscatter. But you see that once you correct for that effect, you get those very credible kind of patterns of a strong jet in the north and some sort of meanders at the bottom. Next is we superimpose this with the SAR image that we have just shown you, which fortuitously was taken just an hour after the airborne data was acquired. And we see this really nice superposition of the jets seen in the Oscar data with the very strong gradients in radar cross-section that we see in the SAR image there. And even here at the bottom, also some of these sort of patterns seem to align with some of the grayscale radar cross-section patterns that we see here. And then last but not least, this is a picture from taken from a high-resolution coastal model that confirms that we have got these patterns of a strong jet to the north. I don't know if you can see my mouse. Strong jet to the north, and also this very strong jet between the islands, and this kind of circular pattern developing here, which we can certainly see very well here. But interestingly, you can see that Oscar and the satellites are kind of suggest the current is actually much further offshore, located much further offshore than the model seems to suggest. So really just to show the kind of the value of these type of observations to validate models, for example. So this is how far we got. Obviously, we still have a lot of OSCAR data to process, particularly for this star pattern further south, co-located with ADCP measurements, for example, and that work is still underway. So I can't show you any of that, but that will hopefully be coming up very, very soon as well. But we're thinking already about our next campaign. So far, all our measurements have been taken in relatively energetic regions, so regions with very strong tidally dominated ocean conditions. And so we'd like to fly OSCAR somewhere else. So we have proposed to ESA to fly OSCAR in the Mediterranean, in what we call OSCAR Med. The funding is not confirmed yet, but we have reasons to be optimistic. I think one reason for this is that it is linking to the SWOT one-day CalVal phase, and we are trying to essentially link up with some of the activities that are taking place in the Mediterranean linked to SWOT as part of the Adopt a Crossover in situ campaigns by the CSWOT 2023 campaign and the BioSWOT Med team as well. And really the aim is to demonstrate OSCAR over a region with less intense tidal currents, in fact, currents dominated by mesoscale and submesoscale sort of variability, which is one of the objectives of SEASTAR, and show if we can actually retrieve fields of vorticity, for example, and whether any of this can links with vertical dynamics and biogeochemistry. So obviously only the beginning of a very, very long story, but this is ultimately the science that we are trying to do with SEASTAR. And oh yes, I just wanted to just say some a word about where SEASTAR would be flying, the general context. So the first red arrow, phase 0, this is where we are now. There are a couple of sort of showstoppers on the way, which I'll say a bit more in a sec. But really, if all goes to plan, SEASTAR would be launched in 2031-32. You can see, unfortunately, we cannot fly, and it's unlikely we'll be flying with SWOT at the same time as SWOT. Even PACE perhaps may not be flying any longer, but there's clearly a lot of interest in these small scale processes as a result of both of those missions. In Europe, we'll have EE10 Harmony, which will be flying pretty much at the time when SEASTAR is launched. And Harmony is also targeting high resolution currents and winds in coastal regions. But there, the sort of complementarity between Harmony and SEASTAR is very much the fact that SEASTAR can offer the sort of much finer temporal resolution to look at, for example, how these processes are evolving in response to weather events, for example, and so on. So this is the particular area we are having to consolidate at the moment, is to demonstrate this kind of complementarity with Harmony. And I guess I ought to put Odysseus as well on this plot when I update it next time. Finally, as I said, so E11, what are the next stages? So as I mentioned, we are currently in phase 0. There's four candidates, and this is where we are still working on refining our requirements, assessing performance, demonstrating the need and the impact, etc., and preparing the report for assessment that will be used for the mission selection. So in October of this year, there will be an user consultation meeting. We don't know yet where, but this will be an open meeting for people to attend, when the 4 missions will be presented to the community and open for discussion, essentially. And this is followed immediately after that by the ASEO selection. So ASEO is the advisory committee on Earth observation that ESA turns to get recommendations as to which mission should go forward. So in October, they will select 2 out of those 4, or up to 2 from those 4 candidates. So we may be one of them, we may not, we don't really know. If we're successful, we enter phase A, where we have another 2 years of studying. And then at the end of September 2025, at the end of 2025, there's another one of those ASEO selection points, when one of those 2 will be selected to go to implementation and launch off in 2031-32. So we are relatively optimistic at the moment that we may have good chance of going into phase A. We are in a really good state. The only thing that could stop us really is if we are outrageously expensive, and we don't know yet what the plan is there on in terms of cost. One reason we are cautiously optimistic is SEASTAR is the only non-atmosphere candidate in E11. The other 3 are all kind of atmospheric missions, if you like. SEASTAR is the only ocean mission, the other only non-atmospheric mission. So hopefully this means that we have a good chance, we're in a good place, and we have a good chance. And after that, well, who knows what will happen. We can just continue to make the case for the mission, and continue to develop its maturity and develop its capability. You can help to make it happen. That's my kind of take-home message. This is currently just a list of the many people who are involved in SEASTAR already. So we have the SEASTAR Mission Advisory Group, which is the advisory group that is advising ESA on the development of the mission. There was this paper in Frontiers as part of Oceanobs 2019. There's many people from the community involved already in supporting the objectives of SEASTAR. And if you want to get involved, please do get in touch, because this is by no means a closed door. There's a lot to do, and there's a lot of potential. And the way you can help is by essentially helping us to build the science case, by identifying key papers, telling us about your results, and which are relevant to SEASTAR, to demonstrate the need. We can share data, tools, set up joint projects, etc., etc. So there's many ways of getting involved. Just contact me, and we'll keep you informed in how SEASTAR is going. I think that is it from me.
Thank you so much, Christine. That was great. And I really appreciate your message about getting involved. I think that's very well aligned with the Odyssey mission message that will succeed if everybody's communicating in the same way.
Yes.
And
yes.
thinking and helping contribute to the science. That's really great. Fabrice has his hand up, so we'll start with Fabrice.
Yeah, thank you very much, Christine, and it's really great to see this talk here, especially coming after last week where we had Dolly Shelton trying to push the idea of measuring divergence, and he was kind of stumbling on the issue that with Odyssey it's going to be Odyssey is going to need a lot of time averaging to get there. But I think SEASTAR is really the kind of instrument that is really designed is more ideal for that. I don't know, if you want to elaborate on that, or somebody else want to elaborate on that. I don't know if you've seen Dolly's talk last week, but I think maybe you can comment on that.
Yes, absolutely. So it is one of the advantages, I think, of SEASTAR is that it's going to help us to learn a lot about other missions, and not just necessarily Odyssea, but I'm thinking also scatterometers who are currently measuring at relatively coarse resolution, but we know that there are all sorts of things happening within the pixel size of the scatterometer. And SEASTAR is going to be able to look at the detail of what's going on and hopefully help us to learn and actually make progress on those other missions. Likewise, imaging SARs, I think, will also benefit greatly from SEASTAR, because at the moment, the traditional SAR systems are measuring just in one direction, which means that they cannot discriminate what is the Doppler signals that we get from the wind and from the currents, for example. So we're really hoping SEASTAR is going to bring a lot of added information that helps us to interpret other types of data. and Odyssea, I guess. I mean, you see the limitation of SEASTAR is that its coverage is limited to those to this cosmos, which means it cannot do a global assessment, and that is why we really need missions who do the global sampling together with sort of these smaller, finer resolution missions that tell you the details of what's going on at these fine scales. So I think, yeah, there's space for all of them. And I certainly don't see any conflict at all between Odyssea and SEASTAR in this respect.
Great. Tony Lee has his hand up.
Yeah.
Hi, Christine.
Hi, Tony.
Thank you very much for the very interesting talk.
Thank you.
I have a question about vertical shear. So to assess model that have, top layer resolution typically much deeper than what's being measured from satellites. Would the strategy for Kelwell be just develop product for what it is, surface currents, or some kind of currents that is tuned to whatever that can be measured by in situ data?
Yes, so thank you. That's a very, very interesting and very difficult question, actually, because we don't actually know that much about vertical shear. And of course, we will be measuring the motion really at the surface. And when we validate those measurements, even for the airborne, we do get differences if we validate it against an ATCP, or if you validate it against an HF radar, or against a surface drifter. So we know that there are issues to do with this validation. And again, we don't have the answers at this stage. All we can do is that we work with people who are looking at these issues of vertical shear and currents. And I think there will be a lot of work needed to determine also how we project the information from the surface into subsurface. That is absolutely for sure. And perhaps some of this sort of information about the vertical dynamics are going to help for that.
Thank you.
Do you have any suggestions?
I'm still trying to learn how to address that question. It's the question that all these mission faces.
Yes. Well, we had the same issue with salinity, because you and I have worked on validating satellite salinity, and we had the same issue there, and we kind of learned a lot about the ocean by having this issue of how do we validate the satellite salinity measurements, which again relate to the top surface. Well, a lot of your validation measurements are at subsurface, and what this is telling you is that actually sometimes the differences that you see are actually real signals. They're not always errors. They are sometimes real signals that tell you something about how the ocean is structured, but even vertical as well.
Right.
Okay.
Yeah. So I guess the question is in a mission concept, whether one want to emphasize that there's a lot that need to be learned about the vertical shear, which can potentially undermine the message of the mission's compelling nature, versus we assume that we can just use the data to validate models that have a deeper first layer without talking about it. Yeah, but that question will come up anyway.
It's always a very delicate balance. These are very innovative measurements, and with all innovative measurements, you have this difficulty where if you already have a lot of information that tells you about what's going on, in a way, it defeats the purpose of having a new mission to measure these things. So, and then if you have very innovative type measurements, then you have the problem of how do you validate it. So, but currents is one thing, but winds is something where we are really scratching our heads. It's how do you validate those winds at such fine resolution? Because these are very, very difficult topics. Winds being even more variable, varying very, very fast spatially and temporally. And what do we know about the variability of the wind at those fine scales? Is there's a lot we don't know.
Right.
And we're an explorer, so we have to continue to play that card. This is by no means an operational mission. This is a discovery mission, really. So yeah, I'll keep our fingers crossed. Thank you very much for your question.
Thank you.
Can I ask Christine about the surface currents and how much Stokes drift might be part of that signal?
Well, in principle, we're measuring the total surface motion. Okay, so in principle, the Stokes drift should be included in this. The slight complexity there is that we are, of course, correcting for the motion of the surface scatterers, which are themselves very much associated with wind waves. So again, this is an area of active research at the moment. A lot of people are looking at this, what is known Doppler wave bias, and how we correct this without taking out the Stokes drift. Because we want to retain the Stokes drift as part of what we measure, but we need to correct for this Doppler wave bias. So yeah, there's many people working on this, for example, in context of Sentinel-1 Doppler centroid anomaly, where there's been a lot of progress there on using those Doppler measurements to try and come up with current measurements. So yeah, it's another very interesting question. Thank you.
And I encourage people to put questions in the chat or raise their hands, but I'll ask another question. You raised the point that winds are pretty rapidly evolving, and that leads to the question, if one weren't constrained to satellite orbits, what would the optimal temporal sampling be at these scales, at the sort of 1 kilometer scale that SEASTAR is targeting?
Yes. Well, I think the scatterometry community is aware that they need, you can't measure just once a day. I think there is a kind of a international coordination happening to try and get measurements of scatterometers throughout the day. I think something like, at the moment, they're achieving something like every 6 hours or so.
That's
so
certainly the goal, to have 4 scatterometers and get the full range of the day.
As you know, the models are run at very, sort of hourly. So yeah, as often as you can. Again, Cygnus was very much hoping to get those measurements. I think it was also 6 hours was the goal for Cygnus to try and get measurements down to that sort of frequency. I think, generally speaking, we have to be realistic and say, with one satellite, you're never going to be able to address the requirements, for example, for operational users who want to assimilate data. With one satellite, you cannot do it. And that is not the objective of this Earth Explorers.
Exactly.
It's about demonstrating capability. And then once the technology has been demonstrated and the need has been demonstrated, then there are other avenues to take this forward into operational context.
Thank you. Tom Farrar has his hand up.
Yeah.
Thanks for the interesting talk. Could you please tell us about the velocity accuracy requirements and the plan to validate the performance of SEASTAR?
So the performance that we've set at the moment is 0.1 meter per second at 1 kilometer. That is coming out of WMO type requirements, but also an acknowledgement about the scales of the currents that we are trying to measure. In terms of validation, we certainly managed to demonstrate that we can reach this in the case of the Wavemill airborne campaign that we did, where we certainly managed to reach this 0.1 meter per second level of uncertainty in RMS error at 1 kilometer resolution against HF radars. We haven't, like I said, for Oscar, we haven't got the results yet, so I can't tell you that. We've also done something which I haven't mentioned at all is the inversion framework which we have set up for this. We are setting up also a framework, numerical inversion framework, where you essentially set up. It's one of those, typical inversion where you define a truth, add some noise, go through the inversion, and so on. And for the system characteristics that we are getting from industry, we have also demonstrated that we can achieve this 0.1 B per second for currents most of the time. Not always. There are configurations when this is going to be more difficult. But typically, yes, we are within the performance requirements that we've set out.
So what kind of measurements will you use to validate the satellite?
To validate, I think our first choice would be HF radars. Again, because we are focusing on coastal kind of measurements, we will have quite a bit of HF radars, HF radar capability to do our validation against. But we'll take everything we can get. So we will also have to do comparisons with whatever else, ADCPs, whatever. No, HF radar, I think, is our number one call, port of call, because of the spatial mapping as well. The fact that we are able to get images from the HF radar.
Thank you.
Does that answer your question, Tom?
Yes, it does. Thank you very much.
Okay.
Any other questions? Tony has a question in the chat. Does the anticipated uncertainty of current depend on wind speed? Yes, of course, yes, but not in the geophysical way, but because of the ability to observe, to retrieve currents and winds is dependent on achieving a sufficient level of coherence in our interferometric measurements, and that is dependent on the signal to noise ratio in our images, essentially, which itself depends on wind. So in cases of very high winds, we will probably have problems. So our typical range of winds that we are hoping to observe on is between 4 meters per second at the low end, and I think 20 meters per second at the high end. Because again, it's a microwave system, so as soon as your wind drops below 3-4 meters per second, you're not going to get very good signals, very good backscatter levels. The coherence will be poor, and therefore you will not have the sufficient quality of data to get the uncertainty that you are seeking. So we have a bit of a problem at the low winds, very low winds, but these are set at a wind speed of, I think, 4 or 5 meters per second. I can't remember exactly, but yes.
Got it. So that number that's listed here, 0.1 meter per second, it's not a weighted kind of uncertainty, not uncertainty weighted average over different wind range, but for more optimal range of wind speed.
It's 0.1 meter per second or 10%, depending, which one's the greatest. So when the current gets higher, of course, that error will increase, but it's not tied directly to wind. No. Although, so this one is, like I say, it's defined at nominal wind conditions. So 4 or 5 meters per second or nominal wind conditions. We're bearing in mind we're in sort of coastal environment where winds may be a bit lower than they would be in the open ocean.
Mm-hmm. Got it. Thank you.
Okay.
Great. Well, thank you so much, Christine. This has been really wonderful.
Thank you.
Exciting to think about SEASTAR and about its potential synergy with Odyssey.
Yes.
and harmony
Thank you.
too.
Yeah, and if you can come to the user consultation meeting, please do, because like I said, on 10-11 of October, there'll be an open meeting when, you know, the whole kind of geophysical community that cares about those 4 missions will come together and essentially, you know, speak up for their missions. So if you are around, it'll be somewhere in Europe, but if you're around, please come along. It'll be great to, you know, to have as many supporting voices as possible.
What is the format for that meeting? Is it in person only?
I don't know yet. Last year we had the UCM for Harmony. That was also, there was hybrid participation as well.
Mm-hmm.
So there may well be a hybrid participation, but the details are not known at this stage. So, but watch this space, put it in your diary.
Yeah, and hybrid participation from the US West Coast can be really grueling.
Yes.
Make the travel seem preferable.
Indeed.
Well, thank you so much. I'm going to stop recording.
Well, thanks again for the invitation and the opportunity to talk. So please, if you have any thoughts about this, please do continue to, you know, interact and email or whatever. And because we, at the moment, like I said, we are very much trying to make the case as strong as we can, the science case as strong as we can. So we're looking for examples and, you know, illustration of need and so on. So if you have good evidence for that, please don't hesitate to bring it to my attention, because we are putting this report for assessment together now over the next few months. So now is the time when it's when things are getting serious. So thank you again.
And likewise for Odyssey. So
I know.
I want to collect the same examples for different
There's
scales.
no reason why not. Indeed.
Yeah. Thank you.